And so last day we talked about what is called the spatial continuous random variables. And today we'll start a new topic, which is known as a multivariate distribution. Multivariate distributions. So in fact, we'll only talk about bivariate distribution, bivariate distributions. So here, what we'll discuss is, you probably have heard of the word random vector, right, or random matrix. So what happens is, suppose we have a sample space. So yeah, so we have a sample space. Let us go back to the point where we started with. So we had a sample space, and then we said, okay, we have a probability measure, and then so there is a probability measure. That means the probability as a function on the sample space, so that we know the probabilities of the individual outcomes if it is discrete. Otherwise, okay, so we define what is called the probability distribution function or density function. So earlier we had the sample space and probability measure. And then we talked about probability density function, cumulative probability distribution function, and so on. And then we talked about what is the probability of an event in terms of probability defined by probability of an event, and the event is defined by random variables. Okay, so we talked about x less equal to some x, okay, or x equal to x, whatever, or maybe so we talked about that, or we talked about probability of a less equal to x less equal to b. Okay, so these are the things we discussed. Now instead of one random variables, one random variable, we have multiple random variables, and that's why it is called a multivariate. Okay, so there are more than one variable. Okay, and here the variable means the random variable. But specifically, we'll focus on bivariate case, meaning we have only two random variables. So there you can, of course, define multiple random variables correspond to the same sample space. Let's say my S is a sample space. Let's say, as we started with discussing an example, let's say we throw, uh, we roll two dice. One is, let's say, a red die, another one, let's say, green die. And then there are possible outcomes here. Okay, and then we have this sample space where if you roll two dice, then okay, we'll have a pair of numbers. Okay, so whatever shows up in each of these die. So yeah, but and then we said, okay, we considered examples like random variable, let's say x, let's say. So here it's like all those pairs a b such that a is 1 to 6 and b is also 1 to 6. And now so and then we define what is called x, okay, which is from s to some r. And say we say, okay, so let's say x is defined by some like s of ab is equal to, let's say, plus b. Okay, the sum of the outcomes. Okay, sum of the numbers which are shown in the dice. So this is one random variable, but you can define, of course, multiple random variable. For example, you can define another random variable, okay, which is like, let's say, a minus b or a times b and so on. So in real life, what happens is, okay, so there is a sample space. So you have made some kind of an observation, okay, and so there are some numbers or whatever the vectors, whatever it is, depending on the situation. And then for each of these vectors, okay, or each of this observation, you are now defining a new number, which is let's say, which talks about, okay, something about the data points. Okay, and then you can define it multiple ways, and then possibly you will look at, okay, how one depends on the other one, or how what is the correlation between these random variables, or what is the correlation between those numbers. For example, I can just consider, okay, let us say your marks in class test, so class test 1, class test 2, and so on. So each of these can be considered as random variables. Okay, or yeah, so each of these can be considered as random variables, or maybe your marks in other courses and so on. So and then try to find out. Let's say I consider x as a random variable. Okay, for x is the total marks in this course. It's the total marks. Okay, in this course, and then I consider, let's say, another course. Okay, a same set of students, let's say, and then in the other course, let's say I have this y, and okay, and then possibly I can talk about, okay, I suppose I want to understand what is the performance overall in this semester in all different courses. So then we have multiple random variables, and we are trying to analyze the correlation between this, or some kind of an influence of whether these random variables, these numbers, the way I defined it here is like the total marks, so that they are somehow okay connected to each other, related to each other or not. Okay, so whenever we have more than one random variable defined on a particular sample space, and the question will be, okay, how they are related, or how we can analyze both the things together. Okay, both the things together. Now once we try to do that, then what happens is, so I have a situation here. Let's say I have some x, okay, and I have some y. Okay, let's say x, y, something like this. So this corresponds to x, okay, and this corresponds to y. So I have possible values here. Okay, suppose I have a pair of discrete random variables. Okay, I have some possible values here, and I have possible values here. Then what I'll try to look at is what are the values here, and what are the probabilities corresponding to each of these values, so that I can try to investigate the connection between this random variables x and y. So here, so that's why when you have only one random variable, it is called univariate case. So here everything, this is univariate when you have only one random variable, univariate. And if you have more than one, it's called multivariate. And if I have two random variables x and y, then this is called say the bivariate case. Okay. Now the thing is, we can write this pair as a vector also, and then it will be treated as a random vector. We can write it this way or this way. So in a random vector kind of a situation, you have a vector where each of these entries, okay, of the vector can be treated as a random variable. Okay, so yeah, so random variable means it is defined on some kind of a sample space, and so these are the corresponding values which it possibly can take. But here, we, instead of writing this vectors notation, because vector notation is used most frequently when you have more than two random variables. So here, the word vector, random matrix, okay, these are used when you have more than two random variables. So here, what we write is we write like x comma y. So this is the bivariate case. So yeah, so this is bivariate. Bivariate meaning there are two random variables associated to this. And then what is the probability distribution when we will be defining it? Okay, so we'll call it the joint probability distribution, because what will happen is for x, if x is a random variable, it has its individual probability distribution. Okay, that is nothing related to, or need not be related to, the distribution or the density function of y. Similarly, since y is also a random variable, okay, in its own right, so y, we can discuss about probability distribution or all the things, or all the concepts, whatever we have defined earlier. We can define it also for y. But when we have a pair of random variables, we have to define everything in terms of a pair. Okay, and what I will do here is actually all the concepts whatever we have defined, we'll just extend it to a two-dimensional thing. So like all pairs x comma y. Okay, and then we'll see. So first of all, let us define what is called a joint probability distribution. Okay, so this are probability distribution, or you can say, yeah, probability distribution when both x and y are let's say discrete random variable. So when x and y are discrete, discrete random variables. I'll give you examples also, okay? Then the joint probability distribution. So joint word is very, very important. Joint probability distribution is defined as a function f of, let's say, xy, which is probability of x equal to x and y is equal to y. So then x, the small x and the small y, they are the realizations of some values, okay, corresponding to x random variable, and y is a realization for the random variable y, okay. And if x and y, these are, I mean, capital X and capital Y, if these are continuous random variable, okay, then f of xy, okay, f of xy is kind of values, okay, for a kind of a curve or kind of a surface, okay, which is on the xy plane, and then the joint density function, okay, is defined. So we'll call this as a joint density function. This is called a joint density function. Joint density function of the pair xy, let's say, if and only if, okay, probability of, just the way we defined actually for the case of one random variable, single random variable, it is in terms of just double integration f of xy dx dy. So what is happening here is, so you have this, let's say, you have this x-axis, let's say here, y, or maybe x-axis here, y-axis here, and here we have some z-axis, okay, and then here is the plane, okay, and suppose you consider some particular portion of this, okay, some particular portion of this, and this is, let's say, a. Then what is that? So there will be a function, okay. So probability that is xy. So these are the realizations, let's say. These are the values here on the x-axis. These are the realization. The values are here. These are the possible realizations of y. And if I take any a from this xy plane, then what is the probability that xy belongs to a? So yeah, so then it is nothing but you'd have to take the integration, and you have to find the value. We'll talk about that again, but let me just introduce all the definitions, because they are just about the extension of just the single random variable case. So once we have that, so similarly, we can ask a similar question, which we ask for the single random variable, that, okay, can any function can be treated as, I mean, can any function be treated as a probability distribution function? Of course, the answer is no. So the conditions for a function to be a function, let's say function f of xy, okay, to be a PDF, or probability density function or distribution function. Okay, for the case of discrete, as we have seen that, okay, so the function has to be non-negative. So here also the same thing, that f of xy should be bigger or equal to 0. And second thing was, okay, sum over all x and y. What are the values of xy, the relations of x and y? So this has to be equal to 1. So, and for the case of continuous, the same thing, but instead of this some double summation, okay, we'll have just integration. Okay, so this is bigger or equal to 0. And second thing, okay, fxy equal to fxy dx dy is equal to 1. So this is the only difference, otherwise everything is same. And then, okay, here of course you can say this x and y, they are from like minus infinity to infinity and minus infinity to infinity. So this is the condition under, I mean, if a function satisfies that, then it can be treated as a PDF. Okay, then we defined what is something called cumulative distribution function, or just a distribution function. So let us introduce the definition, but here we'll just say joint distribution function. Joint distribution function. So if xy are complex, okay, so, sorry, not complex, but discrete. So then we'll define this capital F of xy. So this will be, we'll say probability of x less equal to x and y less equal to y. Okay, the same way we defined it for the case of single random variable. So it is nothing but f of the values of this when t is less or less equal to y, and let's say s is less equal to x. Okay, for any value of x and y. So I can say minus infinity less than x less than infinity, minus infinity less than y less than infinity. So this is for discrete case. Okay, this is for discrete pair for discrete xy. And if it is continuous, this function the same thing. So minus infinity to, so instead of this summation, it will be replaced by integration minus infinity to x minus infinity to y f of st ds dt, and xy could be anything. So this is x less than infinity minus infinity less than y less than infinity. So this is called the joint distribution function. Okay, so yeah, let us see an example. So for example, let's say, suppose, okay, suppose f of xy, this is given to you. Okay, this is suppose this is equal to something like 3 by 5 x y plus x, where 0 less than x less than 1, 0 less than y less than 2, and 0 elsewhere, 0 otherwise. Okay, so suppose this is the PDF probability density function. This is for continuous random variable, let's say. PDF of a pair, or let's say joint PDF of the pair x comma y. Suppose I ask to calculate, find probability of this event, probability of let's say x comma y that belongs to A. Let me say where A is equal to set of all xy. Okay, so such that 0 less than x less than half and 1 less than y less than half. So it's a yeah. So this is the question. So what is given to you? That you are supplied with the density function, the joint density function, and you just have to calculate this integration. So we can just use the formula here. Okay, see the formula or the definition here. Yeah, this was our definition. So this was our definition. So we just have to integrate this, and that's it. So let us just do that. What is happening? Yeah. So we want to find out probability of xy belongs to A, which is probability of 0 less than x less than half and 0 less than y less than let's say, what was it, 2. Okay, so this was 2. Anything, I mean, whatever you can write. So 2. So this will be nothing but 1 to 2, 0 to half, and then 3 by 5 x y plus x dx dy, and you can just perform the integration and you can find out the answer 1 to 2, and then this will be 3x squared y by 10 plus 3x cubed by 15. Okay, and 0 to half, and then dy, and if you just do the calculation you'll get some values. Okay, so yeah, some value you'll get. So the same thing, I mean, instead of just single integration, we have just two integration, so double integration, that's what it is. Now there is a catch here. Okay, so the thing is, we had,
Why
yeah,
1 to 2 for y?
no, oh, limit, what was that? Would you wrote, oh, whatever, the 0 to 2. Oh, here I wrote 1 to 2. Anyway, so okay, so let's say it is 1 to 2. Okay, yeah, so whatever the domain is, yeah. So now there is a catch here. So sometimes we say, okay, so there is a relation when we talked about single random variable, like how do you obtain the PDF from the cumulative PDF, right? So we had this for a single variable. We had so connection finding. Just a minute. So what we had earlier is like, okay, so this PDF can be obtained from the cumulative PDF by doing this. Now just taking the derivative. Now here we have a different kind of situation. We have this f of xy. Okay, then the question is, can we find out xy in terms of this? So okay, so we'll assume that that partial derivative exists. If it exists, then we will say, so there is a catch here if partial derivative exists. Similarly, thing here is like if derivative exists. So instead of that here, if partial, what is happening? Okay, so if partial derivatives exist, okay, so then we can similarly find PDF from the cumulative PDF. Okay, for example, let us see an example. Suppose we are supplied with the cumulative PDF. Okay, or the probability distribution function this as this. Let's say 1 minus e to the power minus x something. I mean 1 minus e to the power minus y when x is greater than 0, y is greater than 0, and 0 otherwise. So this is suppose it is given to me, and then the question is like find the probability density function, okay, and determine, let's say, determine probability of 1 less x less 3, 1 less than y less than 2. Okay, so you just have to take the partial derivatives, and okay, so we have to just take del 2 and del x del y of fxy. Okay, and now there is another question. I mean, if you just recall math 1, okay, so there was like this need not be equal to del square del y del x. Okay, that need not be equal to that. I mean, this need not be equal to del square del y del x. But here, okay, so here we'll assume that so these will be equal if partial derivative exists and they are continuous. Okay, so if we have the same thing, then we always say, okay, we these are equal, and that's how we can get PDF. Okay, so we'll assume that okay, that they exist and they are continuous. So life is simple, and then we can have this. Because otherwise there will be a problem like, okay, whether I'll take the derivative with respect to y first or x first. Okay, because that derivative can be different. Okay, but this will be different. That need not be equal only when, okay, the partial derivatives, they are not continuous. So here also we are assuming that they are continuous. So we have one solution only. Yeah, so if you do that, then okay, so this will be something. I mean, so when x, y are positive, okay, you'll get something and 0 otherwise. So if you take the derivative, I think it should be e to the power minus x plus y when x is bigger than 0, y is bigger than 0, and 0 otherwise. Okay, and then suppose you need to calculate this probability, then you use the same formula. Just you have to calculate the integration. Okay, double integration. Okay, yeah. So what is happening here? So when you have a random variable, okay, let's say, I mean, it is simple to say that what is, so because, I mean, what is the geometric meaning of this? Because when you said, okay, in the single variable case, okay, we had some x here, let's say it is a discrete case, then we had these corresponding values. Or if it is continuous, let's say we said something like that, something is there, okay, and then let's say I want to calculate, suppose a to b, then we have calculated the area. This is how the probability was defined, okay, for the continuous case. And for the discrete case, of course, you just take the sum of all these values, and that can also be interpreted as this integration when we talk about the what is called that the diagram. Okay, what is called the histogram. The histogram. If you consider the histogram, then that will have the same interpretation. But here, what is happening is here we have x, and here x, and this is y, and let's say this is like p of xy kind of a thing. Okay, so this is something like a z-axis. Okay, well, let's say this is this, or maybe it is just kind of, suppose you have some domain, then you have this probability values if it is a discrete case. Okay, otherwise what you can say is like, okay, there is already a kind of some. So this is kind of a density function, joint density function, which is already given to you. So this is kind of a surface. Then if we take a particular area here, like this is my A, then what we'll do is we'll see what are the values here on the top. Okay, this is the values of, let's say, f of xy, let's say. Okay, so then so this is f is, okay, let me draw this like this. Okay, so let's say I have this kind of a situation. Okay, yeah, this kind of a situation, let's say. Okay, and this is how it is defined, and it is it is everywhere, let's say it is 0. So this is my function f of xy. So this is a surface, basically this is a surface f of xy. Okay, and this is y, and this is some f of xy. Let's say I have this. Then the thing is, okay, suppose I am taking some a here, then the thing will be the probability here is nothing but the volume. Okay, volume here. Okay, so let's say this, if you project this, okay, so this is the volume. Okay, so volume of this part is actually the probability. So here, whenever we had the area interpretation for when the PDF is given to you, so let's say this is fx. Okay, this was just a curve here, f of xy, which is a surface. So this is called, sometimes called probability surface. Okay, so this is a surface, and here we have the volume, okay, as the probability. Okay, so yeah, so this is probability here. Let me write it. Probability is the volume under the surface. Okay, so basically, yeah, so I think, yeah, so here, whenever we said it is a PDF, so then we said, okay, this entire area should be equal to 1, and here is the same thing. The volume of the entire, let's say, space, okay, which is under the roof, under the surface, okay, that has to be 1. And if I give you any kind of a subset of the sample space, okay, then the probability for xy to belong to this particular surface, okay, is nothing but the volume, okay, under the surface, okay, on this, projecting on this particular set A. So yeah, so this is the geometrical interpretation of joint probability distribution. Now, another thing to notice here is, okay, and this is a big thing. The question here is, okay, what we are saying, we have to observe this carefully. So we had a sample space S. So let's say this is my sample space. Now we have one random variable X here. We had one random variable Y here. So that means they are taking some values, let's say here, okay, some real number, let's say. So this X is, let's say, the map. This is the real line. This is the real line, and Y is the map. So we have these different numbers maybe here, okay. Okay, then I mean, they need not be distinct. I mean, this can have the same values, okay. So it is not a thing. I mean, yeah, so they can take the same values also. It is not a problem. So this is X and that is Y, okay. Now, if I treat this random variable as an individual random variable, it has everything. It has its probability density, probability distribution, whatever it is. Now, if I treat this y as a random variable, then it has the same thing, the probability distribution and this and that. Now, what we said is, okay, instead of doing this, let us consider a space here, which is x and which is y. And then these values are actually here. Okay, these values are actually here. Okay, these values are actually here, and these values are actually here. Okay, and then we have the corresponding values here. So basically, these values are here. Okay, these values are here. Whatever, I mean, yeah. So basically, here we have these values or whatever it is. Okay, so this could be anything. So yeah, so like some space, like this is a subset of the xy plane. Okay, So then what we started with? We started with some sample points here in this set. Now for each of this, I have pair of values of xy, a pair of real numbers. Now what we're saying is, okay, so it has its own individual, let's say fx, pdf. Here it has fy, and here it has f of x and y. Now the first question would be how this fxy, this function, I mean, I am writing everything in terms of f only, okay? So just to make a sense that, I mean, you can write it as f, g, and h, not a problem. Maybe we can write it as f, g, and h, not a problem. But they are all PDF, so that's why I was using the same symbol. So one is f, one is g, and one is h. And the first question would be how h is related to f and g. Second question would be, if I know f and if I know g, can we determine h? And third question would be, if I know h, can we determine f and g? Okay, so there are basically three fundamental questions. One is, so the first question is like how h of xy, how this is related to, let's say, fx and gy. This is a fundamental question. And to answer this question, there are two questions. If I know fx and gy, can we determine hxy? And the other question is, if I know h of xy, okay, can we determine f and g? But what is the meaning of f and g? I mean, for it is easy to understand for the case of discrete and numberable. If I know the probability of, so here what we are saying is, if I know the probability that this is happening, so this is what is fx, okay? If I know probability of x equal to x, that means happening, it is taking some value, the capital X is taking some value small x. And if I know gy, that means if I know like y equal to some y, now can we determine h of xy? That means can we determine the joint density function? So both of happening of this, can I say this? And here the question is just the reverse. If I know h, that means if I know how jointly they are distributed, what is the probability? So for the case of discrete and numberable, let's say, if I know how joint probability is defined, like let's say it is height and weight, okay? So let's say, as for the sake of an example, let's say, okay, so let me, I mean, I'm writing a different, this thing, let's say, different picture, let's say, this is, let's say, 5, this is, let's say, 6, and they are the 5.1, 5.2, 5.3, and so on. And let's say this is, this measures the height, okay, and this measures, let's say, the weight, okay. So here, let's say, I have something like 50 kg, and then up to let's say some 55, and then let's say 60, and let's say 65, and let's say 70. Now what I'm saying here is, if I know that what is the probability, okay, suppose I know this value, let's say this measures the probability. So this is the z-axis, this measures the probability, let's say, for the case of discrete. So we have discrete samples. So what is the probability that the height is 5 and the weight is 50? I know this value. Now, suppose I also know what is the probability that weight is 55 and height is, let's say, 5. Okay, some value here, let's say, and some value. So something like this I know. Okay, so yeah, something like this I know, let's say. And here also these values are known. Let's say these are possible samples points, and I know this. Then the question will be, if I know this all these values, okay, these are the probabilities, let's say, all these values are known, these are the heights, okay, these are known, then the question will be, from these values, these probability values, can I just forget about y, and can I find out how x is distributed? That means what is the probability that some person will have height 5.5, 5.6, 5.7, or 6 without considering weight? Can I do that? So here you can see whether, I mean, that can be possibly done. I mean, from the intuition, you can say when height probably is not anywhere related to weight, then possibly it can be done. But in general, it may not be done. Okay. I mean, you can speculate. You can have an intuitive answer because I know what is the probability having weight 55 kilo, okay, kilogram, and let's say height is 5 or 6. That value is possibly related, okay, because height and weight maybe they are related, okay, in a generic sense. Okay, so if they are not related, if suppose I have some random, if they are not related, then probably I can find out the probability distribution of a single random variable like weight or height, okay, from this joint distribution. If they are related, probably I'll not be able to find out, and that is what the case is. So this is, in general, the big answer is no. I mean, in general, when I said for some specific cases, it can be said for some specific random variable, but in general, the answer is no. Okay, no in general. That you cannot. Okay, this is the other way. So if we know f, x, and g, y, now suppose this you know and this you know, then the question will be what is how they are jointly distributed. So if you do not know the correlation, if you know how weight and height are related, you possibly will not able to come up with a joint distribution. So this is no in general. That's the answer. I was saying the reverse. Okay, just that's the answer. No, because how weight is distributed, how height is distributed, from there you may not come up with a probability how both are distributed, because you may not know what is the relation between these two. And now here what I was saying is, so can you determine f and g individual distribution from the joint distribution? So here I was saying the reverse, but here I'll show that this is always possible. This is always possible in general. Okay, now here also there is a hint. How can we determine this from the joint distribution if they are not, I do not know about the correlation, like how the values of x, okay, influence the values of y, then how can we determine this individual thing from this individual? The simple answer is you just project it. You just try to project it and see what is happening. So that's a simple intuition, and then we'll try to see, okay, how this can be done. So this is always yes in general. If I know the joint distribution, then I can try to find out the individual distribution, okay, just by projecting it in some sense. Okay, this is not a geometric projection, but in some sense I will project it. So first I'll define it and then I'll see some example. Okay, and this individual distribution from the joint is called the marginal distribution. Okay, so this so something called marginal means individual. Okay, marginal distribution. So I'm trying to go a little fast. Okay, so if you have any doubt, immediately ask me. Okay, so marginal distribution. So let's suppose x and y, okay, let us say they are discrete. Let's say suppose they are discrete random variables. Okay, and let's say f of xy is known. This is the joint probability distribution. Okay, so this is probability of x equal to x and y is equal to y. So this is not for different values of x and y. Then question is, from here, how do you determine the marginal distribution? So what is the distribution of x and what is the distribution of y? Okay, so this is my definition, how you can find it. Then I'll define gx, okay, which is sum over all y, f of xy. This will be, so what I'm trying to do here is, if you just want to find out this, probability of this, so that means you want to find a probability of this independent of this value of y. So that means whatever the values of y, these are the possible values, you just sum this up and define a corresponding value here. So sum these heights, okay, take a summation of these heights here, okay, and add it up. That's how you will get this particular value. Similar thing is, if you want to find for this is x equal to x1, suppose this is x equal to x1, this is x equal to x2. You do the same thing. You consider all possible this, and then you find out the heights and take the sum of all the heights, and then you define that to be okay for x2. This is the corresponding probability. This is how it is defined. So gx over all y, you just sum it up, and that's how you will get this for all x. For all x, and similarly, okay. So this is called the marginal distribution. So the individual distribution, marginal distribution of x and hy. Let's say I define another function. So same thing for the other random variable over this overall x, f of xy, okay, for each y, okay, is called the marginal distribution. Marginal distribution of y. Okay, so this is the case when we have discrete random variables. Okay, so these things are defined when it is yeah, okay, we already said it. Yeah, it is discrete random variable. Okay, now if x and y are continuous, okay, are continuous random variables, then the marginal distribution same thing, just summation will be replaced by integration. So is defined by gx of x is gx, which is minus infinity to infinity f of xy, okay, dy. And for any x, this can be defined similarly. Marginal distribution of y is this h of y equal to minus infinity to infinity f of xy dx. So take all the sum over all the x, and that's how we'll get this y less than infinity. Okay. So let us see let us see a quick example for the discrete case. Okay, this is for discrete. Let's say the possible value of x, okay, are like 0, 1, and 2. Let's say the possible values of y, let's say, are also 0, 1, 2. I mean, this is a cooked up example. So let's say they have the same. So this is y. Okay, and let's say I know this probability. So probability of x equal to 0, y equal to 0 is 1 by 6. Probability of x equal to 1, y equal to 0 is 1 by 3. So this is a kind of a table, 1 by 12, and then 2 by 9, 1 by 6, then 1 by 36, let's say. So if you just sum up all these values inside the table, okay, so these are the probabilities, okay, inside the table. So I am saying that probability, so let's say this is a matrix, okay, and the ijth entry is nothing but probability x equal to I and y equal to j for all ij. Okay, so this is known to me. So yeah, and so if you just sum it up, all these values, so that will definitely give you 1 because it's a probability distribution function. Now, if I want to calculate what is gx, that means what is the distribution of x, and what I have to do, I want to find out probability of, let's say I want to calculate probability of x equal to x. Okay, so for x equal to 0, I just sum it up, these numbers. Okay, then I'll get the value 5 by 12. And then x equal to 1, I'll just sum it up, all these values. So I'll get half. And here, just one value. So this is 1 by 12. So this is actually the probability of x. So you just have to take the sum. So this is what the projection I was talking about. Similarly, if you want to find out probability of y equal to y, so you have to take sum this value, like just summation of add this value. So it is 7 by 12 when y equal to 0. Then you have 2 by 9 plus 1 by 6, which is 7 by 18. Okay, for y equal to small y equal to 1, and then you have 1 by 36. And now you see, if you just sum it up, all these values, so this will be 6. Yeah, so this will be 1, sum of this, will give you 1, and sum of this also will give you 1. So that means that is the function, okay? Because it has to satisfy the condition sum of this. I mean, this is fx, it is what gx, and it is, let's say, hy, okay? So sum of a gx over all x would be equal to 1, sum of hy over all y would be equal to 1. So this is preserved. So they are the marginal probability distributions of x and y. Same thing, I can do it for a continuous case, okay? So for example, so this is, let's say, for the case of continuous, okay, suppose I have this f of xy, which is, let's say, 2 by 3 x plus 2y, when 0 is less than x less than 1, 0 is less than y less than 1, and 0 otherwise. And the question is to find out the marginal distribution, okay, of x and y. So then, okay, you can calculate gx, which is nothing but minus infinity to infinity f of xy dy, okay, and so 0 to 1, okay, so 0 to 1, because otherwise it is 0. fxy is 2 by 3 x plus 2y and dy, and you can find out the answer. Similarly, you can find out hy, which is, you can say, 0 to 1 f of xy and dx. So this is how, for the case of continuous random variable, you can find out this marginal distributions of this. Now let us go back to another problem. Okay, so again, you recall what we said. Okay, now here this is x and this is y, let's say. So x are the corresponding values here, okay, let's say, and y are the corresponding values here, let's say. So we have this possible numbers, let's say, here. Okay, and suppose the heights are known, the heights are the probability. So suppose we are having a discrete case, so we have all the heights which are known, let's say. Okay, some values, these are known. Now if I ask the following question, okay, so this question was not there when we had a single random variable. Suppose my original, suppose it measures height, and this measures weight of the same person. Oops. Oh, everything got deleted or what? Guys, can you see the slide? Can you see the note?
Yes, sir, we can see them.
Yeah, I think it got deleted somehow. I clicked something, I don't know. Anyway, so what I was talking about, I don't know. Actually, I don't see what I was doing here. Okay, so maybe you can see watch the video. I don't know. Anyway, so we had this, and so this is how I was talking about x, and this is y, and this is, let's say, the probability. Okay, the f of xy. Now we have the values here, possible values, and let's say these are the possible values of y. Then we have this. Okay, and we suppose we know the heights correspond to all these values. Okay, now, so this was height, and this is weight. Now suppose, so we said what? We talked about joint probability distribution, and then we talked about marginal probability distribution. Now I am interested to know something else. Suppose I fix this value, that this is the value of y. Then my question is how x is distributed. Earlier, we talked about joint distribution, joint probability distribution, or joint density function. Then we said marginal. Marginal means either you were considering joint, in a joint distribution, you are considering both values of x and y. Marginal means you are forgetting about what are the values of one particular random variable. Now I'm saying no, you don't have to forget, but you fix one value of. Suppose this value is observed, then the question is how this is distributed. So when this is observed, then how, what are the values here? What are the heights here? This is what I want to know now. So that means there are two random variables and there is a conditional thing. So X has some values, let's say height. So my question is now, okay, if height, what is the probability that height is, let's say 5 feet and weight is 50 kg? Height is 5 point, let's say 1 and weight is 50 kg. These are all no, these are joint for all possible values. Okay, now my question is different. Say for the case of marginal, my question was forget about weight. I want to find out how X is how the heights are distributed. Okay, second question. My third question is, which is called the conditional distribution, meaning suppose somehow I know that height is 50. This is fixed. Then how the suppose the weight is fixed. Weight is 50 kg. Then how the heights are distributed? What are the probability then? If I fix the height, a weight to be equal to 50, then what is the probability that somebody will have height 5.1? So this is a different set of different question. And this notion is known as conditional distribution. In fact, you will see conditional distribution. So you will see that in real data analysis, like when you are analyzing a real data, then there will be multiple random variables. So X, Y, Z, or you can write X1, X2, let's say X3, X4, X5. Okay. And all together you will have some value. That is a joint value. Some probability you possibly could define. Then the question will be, which random variable is influencing which one? So then you will try to find out the conditional distribution. Like if I fix this, whether the values are changing or not, or is it keeping it invariant? Okay, for example, let's say you have, let's say you are doing a Google search. Okay, you're doing a Google search. You write something. Let's say I write, okay, so maybe the ranking of IIT Kharagpur in some by some kind of a company or something like that. Okay, ranking is a very bad idea, but anyway, suppose one is interested about this ranking. So you write a big sentence here. Okay, so this is my Google search. You write something here. Then there will be certain links. Okay, here there will be certain links. Now suppose you skip this. So certain links means what? What it is doing. So there are a lot of PDFs, let's say. All these links are, let's say, PDF or web pages. It could be anything, but let us stick to PDF because you're searching only PDFs, let's say. And each PDF is somehow digitalized such that when you are writing all these keywords, these are, let's say, keywords in the Google search. So those keywords are inside those PDFs. That means those PDFs contain those keywords, and that's how it is producing this. Okay. Now let us see, if I forget about one particular keyword or forget, let us remove one of those keywords. Now, yes.
Sir, sir, the
Yes, yes.
sir, the cross marks you wrote all are individually. This is the one of only one.
Which one? Here?
Sir,
Or
the
the,
dots you wrote in the box. No, sir, in the second
oh,
line.
here. No, I'll come to that. I'll come to that. So here, right now, I have no random variable. I'm just giving an example. So because what happens in reality, you have to define your own random variable, which you are interested in. No, I am trying to give you a data, and then we have to define what are the random variables, and then we have to see how one is influencing other one. So we have to make a framework of a model, mathematical model, and then only we will talk about this. Okay, so what happens in real life is you have a problem. Okay, and now it is up to you how do you define a mathematical model on this so that you can calculate something. So the random variable is not given to you. Some data is given to you, and you want to analyze the data. So you can analyze many things, right, about the data. So based on what you want to analyze, you can define your own random variable and try to see. Okay. Now I am giving you a setup where you can have a data. So let us say, so in the Google search, you are these are all the keywords. So these are, you can say, the words. Okay, you are giving, and here they are giving you some kind of links, or let's say some kind of PDFs. What I'm saying here is how, let's say, whatever the procedure Google follows does not matter, but it will produce some kind of web pages or some kind of PDFs. And all these PDFs or all these contents, all these hyperlinks, let's say, and all these links or web pages, they will contain most of these words, let's say, most of these words. Okay. Now I remove some of the words, like say I remove these two words. And now I am checking whether it is influencing my ranking or not, my ranking or my appearances of web pages or not. So that is what I'm trying to see here, whether in this query, these two words are playing a significant role in order to order, because there's an ordering. Why? This first link is something, right? Second link is something. First and second means because it appears first, then it appears second, then it appears third. That's what is first link, second links. If you are not bothered about that, then that's a separate issue. But suppose you are bothered about it, that which suppose you have some particular company you want, whenever Google gives, somebody gives a Google search, you want your web page to come first because they will get a lot of hits. Okay, if some people search like that, you want to do that, let's say. So you want to manipulate the Google system such that you will put the keyword in some such a way that your web page will always come first. Okay. So now the thing is, suppose I remove these keywords, okay, and then I am trying to see whether this will affect the appearance of your web page or not. So appearance means the ranking of this or not. If it does not, okay, and it does not change the ranking, that means these words are not significant. That you can observe. Now the question is, I want to model this, that what are the possible keywords which can enhance the ranking of an web page. That's the job now. So I give you a project, or maybe you join a company and say, the company says, okay, do something. Okay, when we are designing the web page, suppose I design my web page, then I have to give some keywords so that people search that. Okay, my web page will come. So my web page contains certain words. Okay. Okay, so that will come. Okay, so this is there in the design, web design. You will see if you just, for example, some HTML link, if you create, you will see that you can fix that. Then the question will be, how do I choose those keywords such that this will come first? Then, so that is a mathematical problem now. So what you have to do, you first have to do some maybe hit and trial and see, okay, suppose I write this and then whether it is coming or not. And then you have to see which word is influencing the ranking, which word, okay, is influencing the ordering of appearance of your web page. Okay, once you fix that, then you treat this, the set of this, let's say these are the sample points. Okay, now, and you try to you have to accumulate enough data of all the PDFs or something, okay, or web pages which contain that data, and then you see when you write everything together, what is the possibility that, what is the probability that, okay, you have your particular web page which you're interested in, let's say, that will appear in the ranking first, second, whatever it is, or maybe some, suppose k number of links, because this company has many hyperlinks, okay, many some sublinks you can say, okay, so that will appear. So you have to do that. So you have this possible sample point. So then we are trying to fix, okay, how it is influencing the ordering. And then you are trying to find out, okay, suppose this is there, okay, suppose the word is there, then how the ranking or how the appearance of the web pages in the Google search is affecting, okay, that when you give a query about with these other words. So that means once I fix this, okay, once I fix this, then I can change this or this or not this or not this, okay, depending on that, how it is affecting my ranking, okay, of the web pages. So then this is also a situation where you are actually calculating the conditional probabilities, meaning I know something and based on that, how things are changing. So it is basically the same thing when we talked about conditional probability. Okay, what was the conditional probability? So we said probability of an event can change if you know something about the event. Okay, so we defined, so this is our original definition, A given B. So the probability of A may change when you know something about B. Okay. So probability of A intersection B, and this is probability of B. And if we said that if this is exactly equal to P of, if this is exactly equal to P of A, then we said, okay, A and B are like independent, right? So the happening of B, the event B is not affecting the happening of A if they are independent. And we have found also the conditions for that. But anyway, so here, this was my original definition of conditional probability. Now see how the same definition will answer our query here as well. Okay. Now see here, A and B are nothing but some X equal to X. So this is A, and then B is Y equal to some Y. And actually I'm looking at this. So I know, suppose this has happened, then how it is influencing this distribution of all X, let's say. So then if I use the same definition of here, the original definition of conditional probability, it is X equal to X, Y equal to Y, and divided by probability of Y is equal to Y. So now here we know everything. So this the numerator part is nothing but the numerator part here is nothing but the joint. Yeah, it is okay. So f of the joint probability distribution here is the marginal distribution. Okay, so now we formally define what is called the conditional distribution. And this case was not there for single variable, because single variable we had only one random variable, but conditional probability was there. And same thing is happening here. So, but this conditional distribution was not there when we talked about single random variable, because it can only happen when we have multiple random variables. So this is conditional distribution. Okay, so yeah, let fxy be the joint PDF for, let's say, discrete pair of random variables xy. Okay, add of course xy, small x only relation of that. Okay, and let's say hy, okay, is the marginal distribution. Hy is the marginal distribution of y at y, let's say. Okay, then now I denote it like this: f of x given y is equal to f of xy by h of y, of course when hy not equal to 0. Okay, now here for all x, so for each x, okay, is known as the conditional distribution of x given y is equal to y. So this part is known only that capital Y is taking some value small y, and how capital X is distributed. Same thing we can do it for if X is known, then what is Y? Okay, similarly we can say this: when X is known, what is the distribution of Y? So we can say f of xy by gx, where gx is the marginal distribution of x, and of course gx is not equal to 0. Okay, so this is okay. I mean, let me define also for actually the same definition for the continuous case also. Okay, for the continuous case, okay, is the same thing. Okay, so instead of this, so the same thing also for, instead of distribution, you just have to say density. That's it. Okay, so instead of distribution, here, we just have to say density. Then it is for the case of continuous. Instead of distribution, you just have to say density. then that's it. Yeah. Okay, now let us see an example probably. Okay, so I think I gave you an example here. We can do the same thing maybe. Oh, I think that example was deleted. That got deleted. Oh no, here. Yeah, let's say this example. Okay, so here this is a joint distribution. This is the joint PDF which is known to me. Then I can just find out the marginal distributions. Okay, and then I can find out the conditional distribution. Okay, so let me just write. Let me write the function here. I think f of xy was 2 by 3 x plus 2y when 0 less than x less than 1 and 0 less than y less than 1 and 0 otherwise. Okay, so I want to find out the conditional distribution. So for that, first of all, I need to find out the marginal distribution. Okay, so what is the marginal distribution of x? So gx is nothing but minus infinity to infinity f of xy dy. Okay, so if I do that, okay, so it will be 0 to 1 because otherwise it is 0. 2 by 3 x plus 2y dy, which will be something like 2 by 3 x plus y. Similarly, I can find out h of y, the marginal distribution of y, which will be 0 to 1, 2 by 3 x plus 2y dx, and this will be 1 by 3, 1 plus 4y. So when I say marginal distribution, so what is happening here, I have to write gx, so it will be equal to 2 by 3 x plus 1, okay, when 0 less than x less than 1 and 0 otherwise, and h of y will be equal, let's say 1 by 3, 1 plus 4 y, 0 less than y less than 1 and 0 otherwise. So this is the definition of this is the calculation of the marginal distribution. Now suppose we are interested to know about the conditional, so then we can write f x given y, so which is f of xy by hy. So here hy is just thing, but this I know everything, right? So you can just write 2 by 3 x plus 2y. So whenever it is 0, the denominator, then it is not defined 1 plus 4, but here it is non-zero, which is equal to 2x plus 4y divided by 1 plus 4y. Okay, you can say same thing whenever x is this, y is anything, whatever it is independent of that. Otherwise it is 0. And yeah. Okay, so first, let me add one question here. So suppose I say, okay, so this is the joint. Now find, suppose I add this question, here. Find probability of x less equal to half when y is equal to half. That was my question. Find this. So that means when y is given the value half, and I want to calculate the cumulative distribution of x up to half. This is what I want to do. So once I find out this f of xy, then now what we can do is, suppose here y is half given to me. So I want to first find out the probability distribution of this random variable. Okay, so y is given to me, and this is for any value, small value of y. So I can say that f of x given half, because this value is given to me. So this will be 2x plus 4 times half, 1 plus 4 times half. So this is equal to 2x plus 2 by 3. Now, suppose I want to find out what is probability of x less equal to half given y is equal to half. Okay, so since this was continuous, so 0 to 1, 2x plus 2 by 3. So you see, once I know, I am treating the entire thing as a random variable, and this is the probability distribution of the random variable. And then we have dx, which will be something like 5 by 12. That's the answer. Okay, so this again, further it can be, yeah. So then the question will be, what is the geometry of this thing?
Excuse me, sir.
Yes.
Sir, here the upper limit should be 1 by 2 as the x is x less
Oh,
than
yeah,
or
yeah,
equal.
yeah. Yeah. You're right. You're right. You're right. Yeah. So what is the geometry of that? This conditional distribution, the same thing. You have this x, you have this y, and this. Let us say assume that this is discrete. Same thing is true for continuous, but discrete is easy to visualize. So let's say for some this different things I am here. Okay, these are the values x. Okay, and this is like y, and let's say some value here y is equal to, let's say the half here, whatever this value is half. So then that means I am interested about this distribution. Okay, so these are the values. So basically I am slicing. So basically I'm interested about this plane here. I'm interested about this plane here. So now whatever, if it is a continuous thing, discrete thing, depending on continuous means there will be a curve, and discrete means there will be some values. Okay, because I'm fixing this, and these are the values of x. So what is this heights? What are the heights here? Let's say this is what I'm looking at. So basically what is happening is conditional means you just take a slice of the surface. So you had a surface and take a slice of the surface, and then it is two-dimensional picture. So this picture is two-dimensional. So if we have, let's say, so how do I do it? So let's say it is something like that. Okay, so some y values, some x values here. So it is just a slice you are talking about, looking at this particular slice. Then whatever you are doing, so that will be basically entire thing, like again is the area, this and that. Okay, so everything is two. So because here it is a two-dimensional picture now, so your origin is fixed here. So this is the thing, this is x-axis here. Okay, this is x-axis and this is y-axis here. I mean there is no y-axis because we have conditional only. So this is x-axis, and this may be the y-axis, this f of xy, this value. So this is the curve now. So it is nothing but take a slice, and then you perform this one-dimensional or univariate case, like we have only one single random variable. So this is also a very, very important concept, which is called is conditional distribution. So basically what we are doing, we first talked about f of xy, then talked about f, let's say gx, gy, and then we talked about f x given some y, or let's say x y given some x. So this is entirely a random variable for a given y. This is entirely a random variable, and this we already know that this is a random variable x corresponding to x, and this we know, let's say this, and this is of course means probability of x equal to x and probability of y equal to y. So this is gx is probability of x equal to x, and gy is probability of y equal to y. So this is a pair of random variables. So here also you can write probability of x, y. Okay, this is capital Y is equal to paired xy. So here it is pair wise, here it is individual. Here is one value is known. So this is probability of x equal to x given y. Or you can just say probability of x when y is equal to y. Similar thing here, probability of y when capital X is equal to small x. So I have changed the random variable here. Okay, so since I have changed it, so we can similarly, okay, we'll talk about that. But before that, this x given y, as we said before, that for the definition of conditional probability, we said a probability of a given b. Okay, so this may not affect the probability of a. Okay, that I know that b had happened, but this need not affect the probability of a. So that could be exactly equal to probability of a. And then we said a and b were independent. Okay, so same thing you can define now for which is called the notion of independence of random variable. Earlier we talked about independence of events. Now events are described by random variables. So now we can talk about independence of random variables. Okay. or we can say independence, okay, of independence of random number. But I'm not writing it's a continuous or discrete because anyway, distribution function will be replaced by density. That's it, the same definition. It means of random variables. So in fact, I can have multiple random variables like x1, x2, xn, okay, or let's say just I have two random variables x and y, okay. Then so it's a pair of random variables. Then I say, and of course there is a probability distribution function or density function, okay. So this is a pair of random variables, and let f of xy denote the joint distribution, g of x denotes the marginal distribution of x, h of y, let's say it is called the marginal distribution of y. Then I'll say then xy, okay, are independent if and only if and only if same thing like f of xy is equal to gx times hy. That's it. So like the way we define for single random variable, how do we define independent events? A probability of A intersection B is nothing but probability of A times probability of B. So same thing here. So this is probability of x equal to x, y equal to y. And this is same thing as saying probability of x equal to x times probability of y equal to y. That means the individual random variables x and y, okay, they are independent because they are not affecting this particular probability, the joint probability. We can actually extend this definition, and most of the concept we have defined only for bivariate random, or that means pair of random variables. But this notion is very easy to extend for, I mean, all are very easy, but this is not there in the syllabus. So we can define, suppose, just to say how to extend this. Suppose x1, x2, because if you do machine learning, you will see x1, x2, xn. Okay, so x1, x2, xn. Let's say tuple. So n tuple. Suppose this is an n tuple of random variables. Okay, random variables, and then we say these are independent. So then x1, x2, dot 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 xn are independent if, of course, the joint distribution x1, x2, let's say this is a joint distribution function. This is the product of the individual ones, like f and xn. Okay, then it is called. Yeah, so if this is the case, then we say that they are all independent. Okay. Okay, now what we'll do is, what do we do next? So once we define for a single random variable, we said, okay, we have PDF, okay, cumulative PDF. This is how it is defined. So we extended this into concepts, and then we said how to quantify, okay, how to quantify different events, okay, in terms of random variables, and we introduced some concepts. For example, we introduced expectation of a random variable, expected value of a random variable. We said moments around the mean or the central moment. These are the concepts we introduced. The thing is, now we'll similarly introduce, we'll introduce the similar concepts for the pair of random variables. Okay, because these are the measures which will quantify different values associated with a pair of random variables. Okay, let us do that. So first, let's say we talk about expectation. Okay, so expectation of a pair of random variables, let's say. Okay, or way we define it, expectation of a function of a pair of random variables, of a function of a random variable. Okay, or you can just say expectation of a pair of random variables are a function of a pair of random variables. Same thing. Okay, I mean same thing means we can introduce that. So what is your guess? What was the expectation for a particular random variable x? It was just sum over x fx x fx, right? This was the definition. Same thing will happen here. What do you think? Or maybe expectation of a function of the random variable. So this was nothing but gx, whatever the way the function is defined, times fx over x. Now we want to define expectation, let's say, of a function of x, y, the pair of random variables. So this will be over x over y, g of x comma y, f of xy. That's it. Same thing. Where this fxy, okay, is the joint PDF, joint probability density function, probability distribution, because it is summation, so it is discrete. Okay, probability distribution function or mass function. Distribution function. This for the case of discrete, and for the case of continuous random variables, g of x comma y. This is minus infinity to infinity, minus infinity to infinity, g of xy, fxy, dx dy. So this is just a simple extension of concept expectation from one random variable to a pair of random variables. Okay. Now we also talked about moments. Moments, we talked about two different kinds of moments. One is moments around the mean and moments around the origin. So let us first talk about moments about the origin. Okay. So moments of a pair of random variables, of course. Moments about just moments, okay, about the origin. You may forget about this also, just we could talk about moments, okay. So earlier we said, okay, what was the concept of moment? Okay, so it was, we said, okay, this is the expectation of some x to the power r. Okay, this is how we denote it as mu r dash. So it's its expectation depending on its discrete or continuous. For example, for discrete, we said, okay, this and fx. Okay, if that is the yeah, so we said yeah, so we defined this to be whatever sum x to the power r, okay, fx and so on. So for the case of discrete and continuous. So now here we have a pair of random variable. So it is not just x to the power r, but x to the power r and y to the power something as well. Okay. So here we are defining now the rth and sth product moment. So earlier we just said moment, now we are calling it a product moment. Because what is happening here is, why this product is nothing but the Cartesian product. Because when everything we are taking in terms of x pair y, this is nothing but like, so let's say these values are like x omega, y omega. So these are real numbers. Our omega is in S. So this is nothing but Cartesian product of the range of x and the range of y. So that product is nothing but the Cartesian product. So the rth and sth product moment about origin, okay, of the random variables, let's say x and y, is denoted by this. Let's say r comma s, and we use the dash notation here. This is expectation of x to the power r, y to the power s, and the way it is defined, just the product, x to the power r, y to the power s, and f of xy. So this is the joint PDF. Okay. So if this is discrete, x and y are discrete, otherwise continuous. Okay, so let me write this as discrete pair xy. And if it's continuous, so instead of this summation, we'll have integration minus infinity to infinity, minus infinity to infinity, x to the power r, y to the power s, f of xy, dx dy, when this xy, they are continuous random variable, continuous. So this is the product moments about the mean. Now say here, if s is equal to 0, if this s equal to 0, okay, then it is nothing but the moment of x. Okay, so we'll denote. So in this as a special case, this I'll just introduce a notation. Mu dash to 1 comma 0 is ex, and mu dash 0 comma 1 is equal to ey, and this will denote not mu but mu x. So this is the expectation of the random variable x, or the mean of the random variable x, and similarly here it is mu of y. This will be my notation. So this is the random variable. So this is the joint one, okay, or the product moment. Here I have individual moment, which is our individual mean. You can say this is expectation value. This is mu x, mu y. Now same thing I can extend to define product moment about the mean. So product moment about the mean. Okay, so here the same thing. So only there will be shift from origin to the mean. So the rth and sth product moment, okay, about the means, okay, of the random variables x and y, okay, is this. We'll write it as without a dash, so mu r comma s. And this is the same thing, expectation of x minus mu x, because for the case of single random variable, it was just this to the power r. Now I have to take a product. It is mu y to the power s. So if I just define the expectation of the function of this random variable x and y, so this is sum of this x. What is happening? Yeah, so this will be summation over x, y, x minus mu x to the power r, y minus mu y to the power s, f of xy. So this is the case. So x and r is like 0, 1, 2. This is discrete. S is like 0, 1, 2, and so on when they are discrete. Okay, when x, y are discrete. And for the continuous case, the same definition, just you have to replace this summation by integration. So this is also expectation of this x minus mu x to the power r, y minus mu y to the power s, and this will be integration minus infinity to infinity, minus infinity to infinity, x minus mu x to the power r, y minus mu y to the power s, f of xy, dx dy. Okay. Now, when x, r, and s are 1, Okay, so for the case of discrete, it has a special name. It's called covariance. Then mu11 is called the covariance, and this is a very important concept of x and y, denoted by, for the case of discrete. Otherwise, it's just called covariance. Covariance x and y denoted by. So what is happening? I'll tell you. Covariance of x, y, or yeah, or sometimes also written c of x, y. Doesn't matter. Okay, so this is an observation. So what is covariance? Okay, so this is also written as sigma xy. This is also written as a sigma of xy. So also written as this way. So there are many notations. Now the thing is, what is my, this is my observation, sigma of xy, let's say, the covariance. So it is, earlier what we had is, okay, x, what was the definition of variance? You can remember, right? What is the definition of variance? Can you remember the definition of variance? Guys, can you hear me?
Yes, sir.
Yes.
You are audible.
Okay, so here now we are defining some similar thing which is called covariance, because there are two random variables. Okay, and yeah, so when R and S are 1, so this is expectation. For the case of discrete, you can say R and S on 1, S are 1. Otherwise, you can just say expectation of x minus mu x times y minus mu x. So then this is expected value of the product, which is xy minus x mu x minus y mu x. This is x mu y, then y mu x, and then plus mu x times mu y. So now expectation is linear, as we discussed before. So this will be equal to expectation of the product xy minus mu y times expectation of x minus mu x expectation of y, and then plus mu of x times mu of y times expectation of the random variable 1, right? So it is the same thing, 1. We proved this earlier. So okay, yeah, so then this will be equal to, yeah, so this will get cancelled. Okay, so ex is again mu x, this is again mu x, and this is again mu y. So let's say this and this get cancelled. So you have e of xy minus mu x mu y, because e of x is nothing but mu x. We introduced the notation earlier. So yeah, so this is, and this also you can say it is mu 1 comma 1 dash minus mu x mu y. So this is what is called the covariance. So let us find some covariance. At least one example we should see. So let's say we have that table which we discussed earlier. Let's say this is x, this is y. Let's say it is 0, 1, 2. This is 0, 1, 2. These are the possible values. And let's say these are the probabilities. So this gives me the joint distribution function, 1 by 12, 2 by 9, 1 by 6, 1 by 36. So, and then we had the individual distribution like 7 by 12, 7 by 18, 1 by 36, 5 by 12, 1 by 2, 1 by 12. And suppose the question is find the covariance. Find the covariance of xy. I just find sigma xy. By the way, what is the meaning of covariance? Why it is important? Okay, that could be homework, but just to look at the thing. Okay, so this is measuring the product of the expected values. Okay, so the thing is how much deviate it, how much it will deviate from the expectation of the product value when this is taken out, the product of the corresponding means. So you will see actually that covariance is positive, meaning when x was, so let's say these values, let's say x is bigger than mu x, okay, y is bigger than mu x. So if you increase x, mu x is, and if you so if you are increasing x, okay, with the values, the way it is increasing x minus mu x, let's say, okay, the probability, okay, and often when you increase the value of y, so for large values of y, let's say, and then different, so there is some values of this expectation, and then the change in the product value. So what I'm trying to tell you is that if there is a high probability that larger values of x will go with larger values of y, and small values of x with small values of y, then the covariance will be positive. And if there's a high probability that large values of x will go with small values of y, and vice versa, then this covariance will be negative. So I'll just say here that you think about it, what is the meaning of this? Like what is the possible meaning of the covariance? Okay, just think about it. Yeah, now, okay, let's say I have this example and I want to calculate the covariance, okay? So then what is it? So first of all, let us find out, because in order to find the covariance, I need these values or these two values, expectation of xy and mu x mu y. So I know x, distribution of x, I can find out mu x. And here I know distribution of y, so I can find out mu y. So only thing I need to do is I need to find the expectation of x times y. So what is the expectation of this? Expectation of x times y, it is nothing but sum over. So this is x to the power r, y to the power s, but here r and s are 1. So it is x times y over all xy, right? And then f of xy. So if I do that, okay, from the table I can see, okay, so 0 time when x, y both are 0, then fxy is 1 by 6, plus when x is 1, y is 0, then it is 1 by 3, plus x is 2, y is 0, then it is 1 by 12. Okay, yeah, and so on. If I do that, okay, if I keep on doing this, what do I get? And then plus what I have, x equal to 0, y equal to 1 times 2 by 9 plus x equal to 1, y equal to 1 by 6 plus x equal to 0, y equal to 2, 1 by 36. So if I do that, okay, this value is something 1 by 6, and I can of course find out mu x, which will be 0 times what are the probabilities? 7 by 12, 7 by 18, 1 by 36, 7 by 12, right? What are my x? Okay, this was my x, right? And this is my y. So x is 0 is 5 by 12. 5 by 12 plus 1 times half plus 2 times 1 by 12. 1 by 12. 2 times 1 by 12. So this will be something 2 by 3. And similarly, you can find mu y. And then we can find out the covariance, just taking the subtraction of the product. A similar thing we also can do for this thing for continuous random variable. Now I'll okay. So if what happens is that exy you have to calculate all the sum, but you don't have to do that if x and y they are independent. So in fact, if x and y are independent, then the covariance is, because covariance measures something like how one random variable influences the other one. Okay, So if they're independent, then definitely the covariance value will be 0. Okay, so this is an observation that if the random variables x and y are independent, then E of product of xy, the expectation of this is exactly equal to the product of the expectations. Okay, so this is mu x mu y, and hence covariance of xy, or you can just write sigma xy. Okay, this is equal to 0 because it is E times xy, E of xy minus this one, minus mu x times mu y, but E of xy is equal to mu x mu y when they are independent. So this will be 0. So covariance is 0 when the random variables are important. However, the converse need not be true. That means covariance 0 does not necessarily mean that the random variables are independent. So I mean, I'll not give you the proof maybe, but the proof is very, very simple. So yeah, you just write it down, then that's it. The definition of this. So okay, let me just write down one line. F of xy. Now f of xy can be split. It can be written as a product of the marginal distributions, and then take the sum individually on x and y, because now you can split this entire function in terms of a function of x and a function of y, and then you'll see that okay, that this is nothing but expectation of x times y is nothing but expectation of x times expectation of y. So this, however, from here, however, the converse need not be true. That is the covariance or the zero covariance. Yeah, the zero covariance. Okay, does not necessarily imply that the corresponding random variables are independent. You can find different examples, but let us skip the example, or maybe let me just give you a quick example. So let us say my x, I mean, I can always cook up an example, okay? So let us say this is x, this is minus 1, 0, 1, and y, let's say minus 1, 0, 1. And let's say these are the probabilities: 1 by 6, 1 by 3, 1 by 6. And let's say these are all 0, 1 by 6, and okay, the same thing, but let me write it this way. So then this is y. Then probability of x will be 1 by 3, 1 by 3, 1 by 3, and it will be 2 by 3, 0, 1 by 3. And then you see that then mu x will be nothing but what? This times minus 1, this times 0, this times plus 1, so 0. Mu y will be this times minus 1, this is 0, this is 1. So minus 2 by 3 plus 1 by 3, this minus 1 by 3. And then covariance, I mean, yeah. So expectation of axy, I need to calculate these also. So this is minus 1 times minus 1 times what? 1 by 6 plus, okay, 0, 0, I'll not calculate. So this time 0, this 0, 0, this, so this I'll not calculate. It will not calculate. This I have to calculate. So, and this I have to calculate. This I have to calculate. Okay, so this will be nothing but 1 times minus 1 times 1 by 6 plus minus 1 times 1 times 1 by 6 plus 1 times 1 times 1 by 6. So then this will be 0. Then you see the covariance of this is nothing but E of xy minus mu x mu y, which is 0 minus 0, which is 0. But you see that it is 0, but they are not independent. So because you can find out, but Why they are not independent? Because this x times y, this is not this. Similarly, you can say, so it is not that the joint is not a product of the marginal. So this times this is not equal to this one. Okay, or this time this is not equal to, yeah, it is equal to, but other places you'll see that this time this, and then this time this time, yeah, this time this also, okay, is not equal to this one. So and so on. So basically I can say that, but f of xy is not equal to gx hy. Okay, at least when x equal to -1, y equal to -1. This is just one example. You can possibly find other examples. So covariance 0 does not necessarily mean that the random variables are independent, but independent random variables means always the covariance is 0. And okay, another thing is that I can extend the definition of independent, because when I gave the definition of independence, I said also it can be seen for x1, x2, xn. So here I have two independent random variables, then the product is equal to the individual product. I mean, expectation of this is nothing but this. Okay, expectation of xy, x times y, what happened? So it is equal to this when they are independent. The same thing can be also done for x1, x2, xn. Okay, so I can just say, I can just state this, that if x1, x2, xn, they are, if these are independent, okay, then the expectation of the product of that x1, x2, xn can be written this as individual product of the individual expectations, x2 dot 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 e of xn. Okay, now we don't have much time, so let us stop here. I'm also tired, so let us stop here. Today also we have to do a little bit fast, okay, and possibly, yeah, possibly next day as well, Monday as well. So anyway, so if you have if you have any questions, you can also write in Microsoft Teams, and yeah, but we have to do a little fast so that we can start statistics as soon as possible. Okay, hopefully by tomorrow we'll be able to do at least the bivariate case, and then possibly I will see how fast, I mean, how quickly I can do. Maybe I'll skip some of the proofs. Today, as I skipped maybe most of the proofs, I just defined and I gave you some examples, and this is how maybe we'll proceed for next 2 days. And then we can start statistics as soon as possible. Okay, so if you have any quick question, you can ask me now.